this morning this morning and early afternoon we had a look at some of the context. We did check that everybody could log in. We run some jobs to generate a set of benchmarking data, hopefully, and we've aggregated that data so that we've managed to get the minimum calculation time and the overall minimum run time. And the next step is to take that data set, take those timings, and compute the performance. Now, if you can remember back before lunch, what we said, what the performance metric we were looking at computing here was the was to get in megapixels per second, okay, from our timing data and from the size of the image, the size of the image in megapixels, and we're going to do that. Yep, sorry, Adam.
Yeah, sorry, I've just realised I don't quite have all the right columns in my aggregated output. I've only got calc min and I don't have size min.
Okay. Sorry, that might be because I've done the wrong thing. So let me load up my. So I've got the same problem because I missed a step. So let me go back to the original benchmark runs CSV. Thank you for spotting that. That's useful. So what I forgot to do when I was doing this. So if I set these to integer, floating point, was to pick an aggregator for the size as well. Now it doesn't matter really which aggregator you pick for the size because all the values are the same. But you do need to pick one. Otherwise, you end up, as Adam's just pointed out, you end up with a situation where you don't have the size column in the aggregated data. So if you remember, we did the size on the calc by using a plus and selecting the min. Excuse me, same on overall, plus and selecting the min. On size, plus you could use whatever you want. Minimum's fine as well here. So let's set min there as well. And then you do Shift F to do the aggregation. So you highlight the cause column to say that's the column you want to aggregate on. Then you press Shift F to aggregate it, and then you get the right thing. Thank you, Adam. That was really useful. You get the size. You get the size min one as well. So and then we can save that in the same way as we did before. Benchmark ag.csv. So apologies for that. That was, and it tells me it already exists. So I want to overwrite. I'm just going to do yes. Okay. So you're right. We need the sheet with the size, the calc time, and the overall min. The other thing I forgot to do there was order it. So I'm going to go to cause and hit the left square bracket and to order it, and I'm going to save it again. Oops, I saved it the wrong thing. I can just press return. Benchmark score ag.csv. It's going to tell me it exists, so I need to write it yes with a Y. Okay, so I hope everybody's managed to get excuse me, the aggregated data to work from. If you've not managed to get an aggregated data sheet, then please let us know in the chat and somebody can come and help you out and make sure you got to that stage. Sorry. So now we're going to compute the performance. I'm going to quit out of here so that we can start from scratch again and follow what's going on. So there's my benchmark ag.csv, which I've just saved, and you'll see it doesn't have the data types anymore because you lose them when you save as a CSV. You can save in other formats which do preserve data types, but we're just working with the CSVs here at the moment. So we're going to create some new columns, excuse me, which have the performance in megapixels per second, which we're going to use in the next section when we analyze the data. To be able to calculate these, we need to make sure that the columns have the right data types. Again, this is always something you need to do if you've loaded up a format that doesn't save the data types of the columns in the first set. So I'm going to go through and make the cause integer, the size min, floating point with a percent, calc min, and overall min percent. Okay, so that's the first step. So they're all recognized as data. We don't need to worry about the count one because we're not going to use it. We're not going to use that in the work we're doing at the moment. Now, to create a new column, you select the column you want to the left of where you want the new column to be, And then it's a bit like Excel. You use equals, and then you type in the titles of the columns you want to use in the calculation you want to do. So in our case, we're going to do, for example, to calculate the calculated performance, we're going to calculate the size over the calc. Over the calc time. So size min over calc min. Okay, and I want it to go to the right of the calc min column. So I'm going to select calc min. Press equals. It does have tab completion, so if I just type a capital C and press tab, then it will fill in the rest of it for me. And I want the size. Sorry, and I've got that wrong because it's the size over the calc. So let me start with S, size over calc. Okay. You can see that appears at the bottom. And then once you're ready with your with the formula you want to use, you just press enter or return. And it gives you this new column that's been calculated. Now you can see it has an assumed type, which is those yellow percents down the side. We can easily we can convert it to a proper floatable column by setting the type to percent as we usually do, which tidies it up a little bit. The other thing we can do is we can rename the column and something more useful for us, and use the up chevron or the little hat symbol to do that. So if I type that, I want to rename this to calc, and it's the performance, and it's the maximum performance because it's computed from the minimum timing. So calc perf max, I'm going to call that one. Okay, so that gives you the performance of the calculation part of the run in megapixels per second, because we've got the size in megapixels divided by the time in seconds. Okay. Can you do the same for, once you've got to that stage, then go ahead and do the same for the overall perf max, computer column called overall perf max in the same way. Okay, I'm going to put up a poll to see where people get to on that. And if you have any questions or run into problems, as always, let us know, please. And you also do the renaming and the setting to a format as well, so it says in the right format. You've created an incorrect column. How do you remove it? Just give me a second. I have to just double check the syntax so I'll give you the right one. Give me a second, I can't quite find the syntax. Okay, so sorry, somebody's typed something. Yeah, so if you've got lots of exclamations, that usually means you've forgotten to set the data type of the column you're doing the calculation from before you started. I'll show you how to remove a data column now. Give me a sec. So when you're in your spreadsheet, if you really want to delete a column, I think you can type. You should be able to type capital C. If you type capital C, that gives you a list of all the different columns and the type of them. And if you move to the column you want to delete and press D, lowercase d, that should delete. So I'm going to delete my calc perf max one that I've just added. Okay. Okay, so you type the column name correctly in the formula. So you could use tab completion to make sure you get the right one. And if you type Q to go back to your original spreadsheet. So I'm going to do that again. So it's size min over calc min and percent and the up chevron. Okay. I computed the overall column there in the same way as I did for the calcperf max, and then saved my data into a CSV file called benchmarkperf.csv. So if you could do that, let's catch up. That'd be great. I did, and also I just wanted to mention about capturing different run details. We'll talk a bit more about what we need for our runs here that maybe isn't in the output from the sharpen program, where we come to look at automating the process of capturing data in a future section. But in some other scenarios, you may need to think about what you're capturing that won't be in the output of the program. So when you're changing things like the number of cores, nodes, OpenMP threads, that's often in the output of the program in most cases. So you usually get that for free. The same for input parameters. Most well-written HPC applications echo back their input parameters to you into the output log, so that you end up with a record of that for free. The ones that are more complicated is when you say comparing different compilers or different compiler options, they tend to not be captured in the output of the programs, though some do. So for example, if you look at GROMACS, a common molecular dynamics application, it does tell you how it's compiled in the program output. But you may need to do some work to capture that. And then comparing performance across different HPC systems is actually the hardest one, because as well as the architecture differences between processors, the hardware that aren't usually captured in the runs, in the output from the program, there's also different compilers, different versions, different setups, and different environment variables, and all those sorts of things that you might need to capture. As always, in everything I've said, I think I keep saying a lot of the time, it spends at least a small amount of time planning and deciding what is important, because there's nothing more disappointing than not capturing the things you need and then having to redo all the work again, because you suddenly realize you're not capturing a detail that you needed later on in the analysis. So we're going to move on now and do the actual analysis to try and make some decisions and make some and try and think of what this tells us about the sharpen application and how we might use it most efficiently on an HPC system, even though it's only a toy problem. Okay. So let's get past that. So the first thing you might want to do after this is to plot performance and have a look at what it looks like. And VisiData, one of the useful things about it, that will be hard to show in the terminal here when you see it on my screen, but you should be able to see it a little bit better probably in your screen, your own screen, is that it can do your quick and dirty plots of what's there. It's nothing that you could use for like publication or anything like that, because it's just using terminal to output the plot as close as possible. But it can be useful to get a good first look, especially without having to write lots of scripting and invoke plotting programs and graphical interfaces and all those sorts of things. So we get back into VisiData, we load up our aggregate data. I've still got mine in the window here with all the things set, so I'm not going to exit out and load it up again. Actually, go on, let's do that, because so it's VisiData benchmark perf.csv, so we can show it from the start. So I'm going to set up cores because I want to plot that as an integer with a hash. And I'm going to do the two performance columns, perf max and overall, calc perf max and overall perf max, and set them as floating points and leave the other ones blank for the moment. Okay, so I've got one integer one and two floating point columns here. Okay. Now we need to tell VisiData which of the columns is going to be the x-axis variable. So if you go to the cores column, hit exclamation mark to say that that's the categorical data, and it should turn blue. You hopefully see my one turn blue there, and to indicate that that's going to be the categorical data we use. And then finally, we plot a graph by typing G and then dot. So that's G followed by a period. And so I'm going to do that. What it might look a bit like to you is that my screen has gone completely blank, but actually, hopefully you'll see it clear on your own screen if you do this, is that there actually are small dots here. So there's a green set of points that go up like this, and there's the red set of points which go along here like this, and they correspond to the performance of the calculation is the green points going up that way, and the overall performance in megapixels per second that goes out that way. What I've done in the on the material is I've replotted this in Excel, so you can actually see what the plots look like a bit more clearly if you can't really see them. You can't really see them on the screen in my terminal. Okay, so you can see actually the performance of the calculation actually really outstrips the performance of the overall calculation. Okay, so VisiData can be useful to get a quick look at the data, but it's not very useful for reducing publication quality plots or anything like that. But it does mean you have to worry about graphics and stuff. So I'm going to quit out of the graph. If I just type Q, that'll take me back to the spreadsheet. Okay. One of the points I wanted to mention here is we plotted the performance, but we didn't plot the timing data here. You can use VisiData to plot the timing data rather than performance. And it says here, look at the plots and say why you'd want to do them. The problem is when you plot timing data, as the times get small, the curves tend to converge together. So even though the performance can be very different, really, because there's less differentiation between the timing generally as performance improves, you can't really see those differences, or you don't get a sense to scale those differences if you plot timing data. That's why it's often usually preferred to plot performance data, because it gives you a better indication of where the differences lie. You know, because although the timing shows some, the performance data is really the same as the timing data in some sense, it's just transformed. It lets you see the differences better. So there's a question here is what this shows, right? You can see the performance of the calculation part of the overall performance look very different. So has anybody got any ideas as to what might be going on here? Why is the overall performance, what could be the reason that the overall performance is so poor compared to the calculation performance? I'm happy to take any ideas. You know, okay, so Adam says it's due to I/O dominating the total time with many cores. Yeah, and that's pretty much right? Or it could be increased work dividing work to the cores. Yes, and that could be a problem too. So what it actually is, both of those things, right, are things that are are essentially a serial overhead. You know, those are things that have to be done for every calculation, no matter how many cores it is in parallel. You know, you always have to load the data in and then divide it up between the parallel processes. So there's this overhead at the start and overhead at the end potentially as well, gathering all the data back and writing it out. Okay, and if you remember back right to the very start this morning, this sounds very similar or very reminiscent of the problem with flying transatlantic. Right, there's these bits at the start and the end that are sequential, and no matter how much you speed up the bit in the middle, which corresponds here to our calculation time, you know, once that gets very small, the two bits that you haven't speeded up start to dominate the calculation. Right, we can do some analysis to actually reveal these things in a bit more detail, or turn it into metrics that allow us to make decisions more clearly based on what's going on. And there are two things here. One, what we really want in the end actually is what's called the parallel efficiency. Sorry, there's a stray bullet point there. I'll need to correct the materials for that. What we really want in the end is something called the parallel efficiency. That's the percentage of the perfect speed up the reserve of a particular core count, right? Because the value of the parallel efficiency allows us to start making decisions about what the right core count is to choose, or what the balance is between efficiency and runtime at particular core counts. To be able to calculate the parallel efficiency, we're going to calculate the speed up on the way. Okay, so we're going to compute the speed up for the maximum calculation and the maximum overall performance columns. So what we want to do is you can take this data that you take the data. You can either do this in VisiData, or you can do it in Excel, or you can do it by hand, whichever method you prefer. Right? The solution shows how to do it in VisiData, and there's an explanation here of how to do how to potentially do this for in VisiData for the CalcPerfMax. So I'll let you have a go at that for, where are we, 1348. So let's have a go at that maybe for 5 to 10 minutes. So I'll check in with people in 5 minutes time at around 5 to 2 and find out where they've got to with this problem, see if they've managed to create some columns that have the speed up, and also add a column for perfect speed up as well, as in the description of the exercise here. So I'll give you 5 minutes to have a go at that. So we'll find out where people are in 5 minutes, and then we'll decide whether we just give you a bit more time or whether we show the solution and move on. Okay. So if you've got, as always, any questions, anything not clear, please let us know, or you need help, or you're stuck with something, please just let us know. Okay, there are a few people who have completed this. For the people who haven't done this, haven't managed this yet, do you want me to walk through the solution, or would you prefer to give you more time? If you've got a preference, just type in the chat. If I don't hear any preferences, I'll probably just. Most people seem to have completed it now, so maybe I'll just go through the solution quickly and go from there. Okay, just write everybody's managed this. So let me stop the poll and do this. So solution here is in VisiData. You could plot the speed up as well, but let me quickly calculate it. So what you actually want for the easiest one's the perfect speed up, and because it's just the same as the number of cores. So what I can do is I can create a column which is just equals cores. That gives me something that's numerical. If I hit the hash to turn it into real integer data, and then use the up arrow to change the name, I'm going to call it perfect speed up. Okay, that only works for this special case where our baseline is on 1 core. Okay, if we'd been, say our baseline had started by 4 cores, it would have to be number of cores over 4 or something like that to be able to get the perfect speed up. So that one's just because because our baseline's on 1 core, that one's super easy. But it would be more complicated, a little bit more complicated if it was the way to get the speed up for the calculation performance. We take the value of the performance and divide it by our baseline value. So in this case, that's going to be CalcPerfMax divided by whatever the value for CalcPerfMax is at my baseline, which is 1 core, which is 0.15 in this case. I'll convert it to floating point. I'll change the name to Calc Speed Up. Okay, and then finally the same for the overall Perfmax. This time it's going to be overall Perfmax divided by whatever the value is at the baseline. So this is 0.14 in my case here. And if I scroll across there, I make a percent, change the name to overall speed up. And I'm going to save that as benchmark speedup.csv to make sure I don't lose it. So Control S. And save as benchmark speedup.csv. Okay. So I can plot that data. Now, if I try to plot at the moment, it's ready, it's set up for plot, but what will happen is it will plot perfect speed up because that's got a numerical data, the performances as well as the speed up. So to just plot the speed up ones, I need to hide these perfmax columns, and you can do that by moving on to them and hitting the minus sign. So I hit the minus sign on them, that just hides them temporarily and removes them from any plotting. So I've done that there, and then it's just G and dot again to plot. Okay, and you probably can't see it on my terminal, but there's a perfect speed up, which is the green one, which is linear, obviously. And there's the calculation speed up, which is the red one, which goes out here, and then down here there's the overall speed up, which is this yellow one. If we look down here, I've replotted them with Excel here, and you can see this. So there's the perfect speed up, calculation speed up, and the overall speed up. And the overall, obviously, the speed ups follow exactly the same trends as our performance curves, because they are just proportional versions of those. So let me get back to here, so I can type Q to go back to my sheet. I can hit GV to reveal my hidden columns. Okay, to get them back. Now, so as I said, the speed up and the performance are the same shape. You know, so why would you use that? Why would you do them? You know, the only difference that when you're they start at 1 because you've rescaled you've rescaled the performance values to be relative to the baseline value. So why do we use the two different metrics in our analysis? So the answer is here, in terms of plotting, there's no real reason to. You know, but if you want to compare to perfect scaling or ideal scaling, then it's useful to have essentially the normalized data, because they can both start at 1. Whereas if you have the performance data, you have a choice about where you put your ideal scaling curve. Okay, plotting performance directly is usually better to showing difference between different setups, different HPC systems, or different software versions, and things like that, because they show the relative performance differences. Whereas if you normalize both of them to their baseline, they're both going to start at 1. You'll see the different scaling performance, but you won't see the difference in the actual performance. So usually if you're visually wanting to inspect what performance looks like, then you plot performance rather than speed up. We need the speed up anyway, because we're to calculate parallel efficiency, and it's an easy way it's a useful thing to have along the way to calculating that. And it's useful to point out the difference between speed up. You know, there are disadvantages to speed up curves, because they don't show the proper relative performance between things that might start from different baselines. But they have advantages in that they reveal this different scaling behavior more clearly between the different curves or plots if they're done properly. Whereas the performance plots have the advantage that they show you the proper relative performance between the different data sets you're looking at, and actually also give an indication of how the scale is. But what we really want here to be able is a metric to make decisions on. And the parallel efficiency is a better metric for actually looking at a numerical value and then making a decision about how we're going to run our application in parallel. So we're going to add some more columns to our spreadsheet, 2 columns. We're going to calculate the calculation parallel efficiency and the overall parallel efficiency. Remember, the parallel efficiency from way back at the start where we defined it is the ratio of the observed speed up to the perfect speed up. Okay, so if you can add a couple of columns that compute them, and then the second part of this exercise, excuse me, is to have a look at those parallel efficiencies and have a think about what is the maximum core count that could be effectively used for the sharpen example in terms of the overall parallel efficiency, but also in terms of the calculation part. You know, what's the maximum number of cores you think is a good choice to run if you were just worried about the calculation part, but also if you're worried about the overall calculation. So we're just after 2 o'clock now, so we'll give you maybe 5 minutes to have a go, and we'll see, because most people were done by 5 minutes last time. So we'll give you 5 minutes to have a go at that, and then we'll see where we are after 5 minutes, and have a chat about what people have found out. Okay, most people responding seem to have managed this. So what I'll do is I'll go on and add them to my spreadsheet, and then we can have a chat about what they mean. A second. So let me just add a column here, which is going to be calc speed up over perfect speed up. I'll make that floating point. I'm going to change the name to calc efficiency. I don't think I could spell. George, do you put is it I before E or not for efficiency? I think I've spelled that wrong all the way through the course now. Totally paranoid.
No, I think it's okay.
No, I thought it was I before E, except that's
Efficiency. Yeah, it's efficiency. That's right.
okay, fine. The English language is totally useless.
Kind of alien to you, isn't it?
Yeah, of course, it's alien to me. I'm from Liverpool. Okay, so overall efficiency. Okay, so let me hide some columns so that I can get the efficiencies on the same screen. There we go. So we've got the calculation for efficiency and the overall efficiency on the same screen there as well. Okay, so what we can see here is you configure the efficiency as a percentage, right? So you can be so this is, you know, for the calculation, it's around 100% efficient. The 1.02 means it's potentially doing slightly better than expected, like superlinear scaling, but that's probably just a rounding error here, I think, because we're rounding to 2 decimal places for computing the efficiencies here. So you always get perfect scaling up to 32 cores with the calculation one. So it's matching the perfect scaling line because it's got 100% parallel efficiency. And then it drops a bit when you go to 64, 128, it goes to 75%. And then when you go to 256 cores, it goes down to 56%. If we look at the overall efficiency, it's much worse. So the scaling starts going down, and this is what we'd expect from looking at the curves beforehand. Starts going down straight away and reduces quite quickly. Did anybody come up with any ideas about what would be good choices and why of how many cores to use based on these parallel efficiency numbers? I know I haven't said anything about why or what choices to make, but I just wondered if people had ideas straight away. No, okay. Well, usually when we're assessing, say, applications for access to Archer 2, I think things like you would tend to be trying to look for parallel efficiencies in terms of core count people are running on of 70% and above, right? I mean, if someone's got parallel efficiency above 90%, it's doing really, really well. If it's above 70%, it's pretty acceptable, you know, and then yeah, okay, cool. Thanks, George. And then if it's below 70%, it may be acceptable in some circumstances. It depends what the balance the person has between the urgency of the need to do the results, the need to get the results, so the time to solution versus the amount of resources they'll use, because you're not making a hugely efficient use of resources. There's also sometimes you get things that don't scale very well, but there's no way you can run the calculation otherwise because you need that amount of distributed memory or that many cores to be able to run within a reasonable time frame. And in those cases, you might have to just accept the lower parallel efficiency than you would ideally. So, you know, here it looks like for this application, remember the application is the combination of the program plus the input data set. Then for the calculation efficiency part, probably anything up to 128 cores looks pretty fine. But overall, in terms of the calculation, actually by the time you're at 4 cores, you probably that's probably in the right area of balance of time to solution versus parallel efficiency. And after that, you're into the realms of rapidly diminishing returns in terms of what you're actually getting when running when using more cores for the calculation. Okay, but as I said, I mean, there is a judgment call here, because we say here, like, less than 60% power efficiency is generally not considered a reasonable use of compute time in normal workflow production. That's because that means 40% of the time you're using is essentially being lost or wasted in terms of the resources you're using. But if the time to solution is critical, or there is no way you can run on a lower core count, then maybe that's just what you have to accept, is that lower parallel efficiency. And one of the reasons we're doing this here is to try and show you that once you've got your performance metrics, then using something like the parallel efficiency, particularly when you're looking at scaling like this, is a useful metric to make decisions on. Whereas you might not have had that. You can look at the performance and say, oh, it's tailing off a bit here. But if you actually look at the parallel efficiency, you can make some concrete statements about what is and isn't acceptable in terms of what you're doing. It allows you to make decisions about what's an efficient way to use the resources you have access to. So I just want to finish off this section where we talked about how to actually get something you can make a decision from. We're going back to the sort of limits to scaling and speed of the parallel efficiency, and this harks back to the discussion we had about airplanes and transatlantic flight right at the start. So first thing I want to mention is there's two different types of scaling people talk about here: strong scaling and weak scaling. What we've been looking at here is strong scaling. That is when the problem size stays the same and you increase the amount of resource being used, or increase the parallelization. So we've increased the number of cores and kept the problem size the same. With weak scaling, you keep the problem size per bit of parallel resource constant as you increase the number of cores. So that means your problem size gets bigger in the same rate that your resource request gets bigger, or your number of cores, or whatever, MPI ranks or nodes or whatever, increases. In general, strong scaling is generally more useful, but more difficult to achieve in practice. So strong scaling is more useful because, say you're modeling the Atlantic Ocean at a certain resolution that makes sense for your research, then the faster you can get that to go, the better, because the more cases you can run, the more parameter sweeps you can do, the more science and research you can do with the same amount of resource, and that's a strong scaling thing. The weak scaling equivalent is, if I had access to more resource, I may be able to study that ocean at higher resolution and resolve features of say, currents and interactions between the seabed and the ocean itself that I might not have otherwise been able to do at a coarser resolution. Okay, so weak scaling can be useful as well, and is critical in terms of a lot of modeling and simulation. But strong scaling is more generally useful, but it's harder to achieve because you have to parallelize a lot more of the code. In terms of the image sharpening example we've been looking at, how would you use the image sharpening exercise to look at the weak scaling performance of the code, and what would have to be changed the way we did the program? Well, you need to be able to have different images, or at least potentially be able to stitch the image we do have together into one bigger image that's made up of 4 copies of it. For example, if you wanted to use four times more cores or something like that, and that would keep the amount of work per processor constant as we increase the number of processors. So the limits of scaling, which are usually measured in terms of parallel efficiency, and the cases of both strong and weak scaling, well understood, right? They've been captured in 2 different laws: Amdahl's law, which talks about strong scaling, and Gustafson's law, which talks about weak scaling. And back in 1967, Gene Amdahl said, the performance of route to gain back parallelization is limited by the proportion of the code which is serial, which is exactly what we've seen here. As some people pointed out, is the serial bits of the code, which is the data input and output and setting up the parallel calculation, eventually become to dominate and limit the scaling of code. So the time for the I/O part, and as George suggested, you can go back and calculate the overall time versus calculation time, and that gives you some sort of measure of what we'll call the I/O time, or you can call the serial time if you want. And you can see that I've done that here. This is the minimum calculation time, the overall calculation time, and if you subtract the calculation of the overall, you get the timing for the serial component. You can see it's essentially static, and it even increases a little bit at the end because it takes longer to set up the calculation across across all the API processes. And then as you increase, as the overall runtime decreases, the fraction of the serial I/O time increases because it's staying static. So eventually, when we get to 256 cores, it's 94% of the runtime is spent in the initialization and shutdown stage as the serial stage of the calculation, which is why it stopped scaling at that sense. And actually, you can sort of calculate theoretically, how much of a code you would need to parallel, how much of the code needs to be parallel and scalable before you run into these limits, and what that means for as you scale up. And the numbers are quite surprising, right? So if we reduce the serial fraction of a code to 1% of the application, we're still limited to a maximum speed of 100 no matter how many cores you use, right? So there's only 1% of your execution time at, say, on a single core is a serial part of the code. Then the maximum speed up you can ever get is 100. Okay, so on Archer 2, you've seen there's 128 cores on a node, and typical calculations generally use more than 1,000 cores. So you can see how much actually hard work has to go into parallelizing applications to be able to achieve strong scaling to thousands of cores. And there's even calculations looking on Archer 2 at using hundreds of thousands of cores, 500,000 cores, say something like that. So the fraction of serial code that has to be left over for scaling to still be viable at those scales in a strong scaling sense anyway, it's quite staggering, really, when you think about it. So for our particular example, we look back at the baseline results on one core, we can see the fraction of the serial work, the I/O part, is actually 8%. Right, so the maximum speed that we could potentially achieve for this application is 1 over 0.08 is 12.5. The maximum speed that we actually observe is around 10. Okay, because the parallel section does not parallelize perfectly at larger core counts due to the parallel overheads. Okay, so even with the maximum parallel efficiency you can achieve, you never quite achieve that anyway. In terms of weak scaling, the serial component doesn't dominate in the same way. So it works much better as you're scaling up to larger cores. So the formula is there, but essentially for an application with a serial fraction of alpha equals 0.01, which is 1% serial on 1,024 cores, that's 8 Archer 2 nodes. The maximum speed ups around is over 1,000, right, and keeps increasing as we increase the core count. So if you contrast that to what you needed to do to achieve good parallel scaling with Amdahl's law in the strong scaling case, you can see why good strong scaling is actually much harder to achieve. But weak scaling is useful, as I say. In a lot of cases you really want to increase the resolution of the model that you're looking at, and that's where weak scaling can really help you out. So there's a question here. You can have a think about it and have a look at the solution if you want, about why we don't always want to use, why weak scaling is not always possible. I've already talked a bit about it. So we're sort of at the end of the sections about gathering the data, or we've gathered the data set, we've analyzed the data set, we've turned it into metrics which we can use to make decisions. Hopefully use that to illustrate some of the challenges around getting good performance, and hopefully giving you some techniques that you can use to actually think about when you're using an HPC system, how you could decide what the right resource set to use is for the calculations, or how to go about actually calculating such a thing. For the next two sections, we've got until the end of the course. Let me scroll back to the top and go back to the overview here. We're going to talk about two things. We'll have a break at some point in the middle as well. So somebody asked about automation earlier and how you might go about automating collection, because obviously what we did was quite manual and was a bit prone to mistakes, and didn't talk about how to collect data, how to collect all the extra bits of information we might need. So we'll talk a bit about that. And then we've got a very short section, or quite a short section at the end, where we look a bit at profiling. And this is just not to do any sort of in-depth profiling, but just to give you an idea of what's available and what sort of information you can get from a profiler. That if you wanted to take the next step beyond this and understand not just what the scaling looks like, but why the scaling looks the way it does, and start to talk about those and think about those sorts of things and how that could be changed and improved. Not necessarily by modifying the code, but potentially by modifying your input parameters to a calculation and things like that. Then what that means. But before we go on to those sorts of next sections, given we're sort of at the end of the sort of performance, the data analysis side, I just wanted to give a chance for anybody to ask questions they may have about what we've done so far, before we move on to the next bit. No? Okay, so hopefully, and there's a bit of information, and it may, the other thing I would say is, if you think of questions after the course and want to get some input on them, please do just email into the Archer 2 service desk. Mention you're on the course. You can even mention my name as the instructor, and any questions will get routed to the right place. We can chat to you. You can even set up Zoom calls or something like that if you've got more in-depth chat you want to have. If you've got some more complicated things or something that would benefit from that. So, if you think of other questions or anything occurs to you after the course, please do get in touch with us. We're happy to help out with any of those sort of follow-on questions. It's one of the reasons why we give people access to the accounts for longer than just the day of the course, is because there's often having the chance to explore what people and practice what you've learned during the course is useful to people, and that often leads to more questions anyway. So what I'll do then is I'll carry on, and we'll go and talk about the automation side of things. Okay, so what we're going to try and look at in this part of the course is, why would you consider automation? I think hopefully that's pretty self-evident, but we'll talk a bit about it. What considerations we need to have when we're automating the collection of performance data, and what tools might be out there to help us. Excuse me. So hopefully you've seen how to collect basic benchmarking data, and you understand a bit about that, and how to analyze it is what we've been doing for the past session. We want to make this simpler, right, and actually less error prone than doing it manually. So it can be pretty onerous and a time-consuming task to collect data, benchmarking data manually, especially if you have a large parameter space to explore. Say you want to vary core count, but you also want to vary some other parameter at the same time, be it an input parameter to your program or something else. So when you have more than just a small number, and it was even pretty tedious running the quite small number we've run in this course so far, it's often worthwhile taking a bit of extra time to start to automate this collection. So in addition to reducing the manual work, it has a few other benefits. One, it makes it more systematic across different parameters, which helps for the analysis and the labeling of data and understanding what data you've got and what data you haven't got. It makes the recording of the details more consistent. It makes it easier to do the automated analysis, and it makes it easier to rerun benchmarks in the future. Say you're on the same system and something changes on it, it gets upgraded, or a new software gets installed that you might think might have a different performance, or you move to a new system. You can take the same benchmark scripts and approaches with you to this new system and rerun what you've got pretty easily, rather than having to do all the manual work again. And there are loads of different ways to do this automation. You can use an existing framework or something that's out there already, create your own scripts, or you can create your own scripts and different ways of doing things. In general, it depends a bit on how much you're going to do, how formal it is, and how complicated it needs to be. If you're going to undertake some really complex benchmarking study with lots of parameters, and it's going to be reused by lots of other people, then using some sort of existing framework and taking the time to build it into that is probably worthwhile. If it's just for you and you're going to do some pretty simple benchmarking, but you want to automate it, then it's probably easier just to write some simple scripts to do that. And the scripts obviously could then be written in anything you want, as Perl, Python, Bash, C, anything, any sort of thing, any sort of approach you want to take. What we're going to look at here is quite a simple approach, because we're trying to put together in this course a way for people to do something relatively quickly and easily to help them use their resources better on an HPC system. Okay, rather than undertake complex benchmarking research they might submit a paper on, something like that. So what we're going to do is we're going to write some simple scripts in Bash, or actually 2 simple scripts in Bash that allow us to automate what we're doing in terms of running the benchmarks at different parameters, and then capturing them, and being able to specify these different parameters. Sorry. So first of all, we need to decide what parameters are varying, and if there's any data we need to capture from the ones that aren't captured in the application itself. As you've seen, the things we've varied are the number of cores and the number of runs at that particular core count. So we did 3, but you might want to do more than that potentially, and you want that actually to be configurable depending on how much time you have on the system and how variable the results are maybe. Things you might need to that are not in the application output, so the date and time of the run. Often applications do include this, but you saw from the sharpen output that it didn't. So we should really think about that, so we can place it in time. Say we have some performance data and something changes on the system at some point. We want to know which performance data is from before that time and which data is from after that time. Okay, and we're going to need to capture the run number at that data point. So is this copy of run number 1, 2, or 3? In our case, that wasn't in the application output, so we need some way to do that as well. Excuse me. We already saw how to use srun directly to run the benchmarks, and one of the participants also posted in the Etherpad a script, batch submission script for how to do it using sbatch rather than srun. That's what we're going to do here. So I'm going to skip over. I'm going to go through this quite quickly, and we're not going to spend the time for you guys to do this exercise. What I'm going to do is show the solution because it's quite similar to what we've done before. So this is a batch submission script that you can, rather than waiting for the output, you can submit to the queue and then come back later and get the output, which is obviously much more what we want to do to automate, because we might want to submit lots of scripts at once and then come back and collect the complete data set afterwards. Okay, so it's got the hash bang at the top. That's what this hash exclamation mark is, that tells it what shell it's running in. In this case, it's bash shell. Okay. These are the various options to the job. You'll recognize most of them from the command line we gave to srun. So for example, there's a time. This time's a bit longer, it's 20 minutes, but it doesn't matter. There's a number of nodes, tasks per node. We've also got the CPUs per task. That's not really interesting in our case, but it's in there for completeness, is what Archer2 recommend goes into the job submission script. The count, the partition, the QoS, and the reservation are all things we had in before. Now, generally, one difference with batch submission scripts compared to the interactive running is that they don't have the same environment that your shell does on the login node. So you need to repeat the commands to set up the environment. There's a special module which is used on the Archer2 compute nodes to configure the environment in the first place. So that needs to be in all job submission scripts on Archer2. And then we need to load this training sharper module, because although we loaded it in our interactive shell with login node, and that made it available to the compute nodes when we ran interactive jobs, when we run a batch job, that environment won't be exported along with the batch job. So we need to do the same again in a batch job to make sure the environment's set up. And then this is the srun command that we had before, similar to what we had before, but it takes all these options from sbatch and then adds on any other ones you want. So this looks very similar to before. We've got the distribution and the hint options, which I explained before, the name of our program, and the output. One thing we've done differently in the output here is before we specified, we wrote down the number of cores. Here, we're using this special environment variable, which is set by the scheduler called slurm, which is the number of tasks in total that this job's being run on. So in this case, because it's one task per node and one node, that's going to come out as 1. But if these numbers here varied, then that would change to match. Okay, so if we change the task per node to 2, then that would go up to 2. If we change the nodes to 2 and the task per node to 128, this would change to 256, because it's the total number of tasks specified by Slurm. Okay, so that's an example job submission script. And let's let me quit out of here. I'm going to create a new directory called sharpen bench auto to put stuff in. Oops. I need to make it first, obviously, before I CD into it. Okay, and the only thing I'll need from the other sharpen bench is the fuzzy image, the input image, which I'm going to copy here as well. So I've got that there. Okay. Then I'm going to create this job submission script. I'm just going to call it submit.slurm because I've got no imagination. And I'm going to copy and paste all this in, and just to show hopefully that this just works. Okay. And this one's at the moment it's hardwired to say run 1. Okay, so that will change at some point. But let's go for that and see what this works. So I submit my job submission script with sbatch submitted SERM. And it tells me that it submitted the batch job. And I can see straight away the output's already there. It's run very, very quickly. So I get this output file, which is what Slurm just gives me always as part of the output. Some data, but because I redirected the output into here, it's in there. So let's look at the output there to check it's doing what we thought it was doing. So that looks exactly the same as what we had for a single core on when we ran it interactively. Okay. So we've got a working job submission script, great. But we actually want things to be able to vary automatically. Okay. So looking at our script, there's a couple of things that we wanted. We want to identify the parameters that vary in the script and write a parameterized submission script. So we need to remember we wanted to vary the number of cores, the run number at this data point, but we also wanted to be able to capture the date and time of the run and the run number at the data point, which isn't in the output by default. Okay, so in our job submission script, this line is in our basic script at least up to 128 cores. This line is the thing that needs to vary. Okay, we may need to increase the number of nodes as well if we're going to go up to 256, but we're not going to worry about that right now. The run number doesn't appear anywhere in our script at the moment, so we need to find a way to include it. When we do this, it always also addresses the fact that we'll capture the run number in the output in some way. And finally, we need to capture the date time in a way that can be used in the output. One of the most convenient ways to do this is to use the date command and use this what's known as Epoch Time, which is a number of seconds since 1970, since the 1st of January 1970. And you can use this command. So you've probably come across the date command, which prints the current date, but it does take options about what format to print the date in. So if you give it the format +%s, you get the number of seconds since the 1st of January 1977, and that gives you a handy timestamp with the resolution of 1 second that you can use in your job, that you use for capturing some sort of automated timestamp to include in your applications and scripts. And as we saw before, you can capture that into a variable that you can use by surrounding the command by parenthesis with a dollar in front of them. So I could do this because this is just bash. I can use these commands on the terminal as well. Okay, so there's the command. Moves it into timestamp, and if I echo now the contents of timestamp, it'll be the number of seconds. You see it's changed slightly from when I ran it previously, and because the time's moved on. Okay, so we've got a way to capture the time, and we need to vary the compute nodes. So what I'm going to do and put this in a run benchmark file is set this thing up. So what I'm going to do is capture it first, and then I'll go through it and explain what's going on here. So, oops. Okay, so this is a bash script. Okay, there's two things. The first thing it does is capture the arguments. If you've only done any bash scripting before, $1 and $2 are special arguments. If I type the name of the script on the command line, or if I ran the script on the command line and then provided some arguments on the command line for the script, they'd be captured in, the first one would be in $1, the second one would be in $2, the third one in $3, $4, $5, $6, and so on and so forth. So if I type, let me save this, just a minute. So if I typed bash run benchmark just to run it, then if I set that'd be the first argument on 1 and 2. They'd get captured into the value 1 would go into $1 and the value 2 would go into $2. Okay. Stop me if anything's not clear and ask questions, you know, if it's not making sense to you. Okay. And then what we're doing is we're piping into SBatch the contents of this. So this is called a here document in Bash, and it says take everything up until you hit the string EOF, end of file in this case, and pipe it into that command, okay, as input. So this is just the same job submission script we had when we just did it without anything varying, just about. Okay. The first thing it does a couple of different things. One is it replaces the tasks per node with the number of cores, which we've read in off the command line here. Okay. It does all the other stuff the same. It loads the modules, all those sort of things. But then it also has a loop which loops over from 1 to the number of runs, which it's captured from the command line at the top there. So there's a special bash command called seq, S-E-Q, that gives you a sequence of numbers from 1 until whatever number you specify. It captures the timestamp using the date command we saw before. And then it issues the srun command and outputs the data to a file which is called bench. The number of tasks, we saw that in our earlier command, that's the total number of tasks specified in the scripts. Run, and it uses the value of the irun variable, which is the number in this loop. And then finally, it adds the timestamp at the end. Okay, so what this does is gives us a parameterized job submission script where we can specify the number of cores we want to use and the number of runs we want to do at that core count, and it will run those for us. So let me save that. So say I wanted to run 3 copies at 1 core. Okay, 1 core. Then I should be able to do bash to make sure it's a bash script. Run benchmark to shush, and it was cores and then runs, I think, wasn't it? So number of cores, then number of runs. So bash. So the number of cores is 1, and I want to do 3 copies of that. Okay. So that'll tell me it's submitted a batch job. And hopefully you'll see, so there's the first run with its timestamp and it's run 1. There's run already. Now it's added the second one, run 2, with a slightly different timestamp, and then run 3 with a different timestamp again. Okay, so we've now created a parameterized job submission script that we can specify on the command line the number of cores we want to use and the number of copies we want to run. Okay, so that's part of the way to automating what we want to do. The second step, so that's just explaining what's going on there. The only thing to be careful of course, is this timing here now, because we're running multiple copies. This time needs to be long enough to run multiple copies. So in this case, we're running 3 copies, but each of them takes 3 seconds or so. So 20 minutes is plenty time enough. But if we were running 30 copies, then you know, it might not, no 30 copies would still fit. If you're on hundreds and hundreds of copies, then it might not fit in the 20 minute time limit. So you might have to vary that. So you need to be a bit careful about. Okay. But now what that means is that we can, because this is Linux, right? And what you tend to do is string everything together, is you can write another bash script that then sets up a list of the core counts we want to run at. In this case, up to 128, because we haven't got a script that deals with multiple nodes yet. And the number of repetitions. And then we can say for every value of core in these core counts, we do something. We actually run our benchmark script with that number of cores and that number of repetitions. And it should submit a job for each of them. So let me copy and paste that and save that in launch benchmark.sh. So I'm going to paste that script in there. Okay, so this is just a list of core counts that we want to run on from 1 to 128. We want 3 repetitions at each core count. And then so we're going to loop over every value in core counts, set the value of cores to the current one, and then run this command. Okay, and we're going to take the value of cores and then rep and repeat it. So let's save that. And now, if I do bash launch benchmark.sh, hopefully you should submit a lot of jobs. Okay, so it's submitted a lot of jobs. I can look at sq-u $user, which is my username. And you can see they're all there and running away, all on one node, of course, because we haven't got more than one node. And they've all finished. And what you should see is that with that simple script, I now have 3 copies at each one of those core counts. And hopefully, if let me remove the rogue ones, which is this one we own first of all, and the slurm.outs. So now I should be able to test this with my sharpen data.py Python script. And we have the full data set, apart from the fact that our original data set, we use 2 nodes and 256 cores as well. But we essentially have generated the full data set with one command, okay, which was this bash launch benchmark.sh, which then looped over and called our run benchmark.sh script multiple times. And better than that, it's also captured for us the timestamps of when each of these copies ran. So we know exactly when they ran as well, because you can always convert between Epoch Time and real time. There's lots of utility in that. Okay. So one thing that you could have a go at if you wanted to is modify the parameterized submission script to allow for multi-node runs. So that's specifying, as well as specifying number of cores, number of cores per node, it should also specify the number of nodes you want to use. So can I let people have a go at that for, what are we, 46? Let people have a go at that for 5 to 10 minutes, and then we'll see where we are. And then we'll probably be stopping for a break for a wee while to give people a chance to get a drink, stretch their legs and stuff before coming back for the final session. We'll have a bit of a look at basic profiling. Do people have questions on what we've just seen there in terms of automation? Did that make sense to people, or is there things that aren't clear? So Owen, I wonder if it's because you've got 2 partition specifications in there. So I can see partition near the top and partition near the bottom. So I wonder if the fact that partition is put there twice is confusing it. I don't see why that should be, why it shouldn't like partition twice, but I can try that. If I put it in twice here, no, it seemed to work for me. So is that with the automatically parameterized one, or with the one where the task per node and stuff are hard coded into it? Okay. That is weird. The only other thing I can think of is that some weird characters. Look, George has found something. Yeah, no, I said that, but I've just tried that on my script. And I put partition twice into there, and it worked. Yeah, so this has partition standard twice in it, and it worked fine. So
Which script are we trying to run? Sorry.
so this is just a hardwired one, not a parameterized one.
Oh, okay. There's no minus partition specified in the srun command, is there?
No, you shouldn't need that. And that's not the
No,
error
but
anyway.
I'm wondering if
It's
there
not
is
the
one.
SBAC error. So it's okay. So Owen, can you try just copying that script into your space and try submitting it with. And that'll tell us whether it's something to do with your account or whether it's something to do with the script. Because if that one works, it's something to do with the script.
I'll try that too, just to be thorough.
In fact, you should just be able to do. That, Owen, it's SBatch, not SRun. I think that's
The
the problem.
SBatch version does work, yeah. It's not a very helpful error from Slurm yet again, though.
No, that isn't very useful at all in terms of telling you what's actually going wrong.
I also notice it looks like you need to remove all the slurm.outs before you run the Python data processor thing.
Because they're called out.
Otherwise, it tries to process those and can't get what it wants.
Yeah, you could. The easiest way is probably actually to change the extension in the run benchmark. Sure.
Oh, okay.
So if you change that to .dat, then you could specify an action. Oops.
Like you don't have to remove your slurm
then
outputs.
You don't have to. Then you have to worry about your slurm outputs. That's probably an improvement to make to the course materials. Right. So let me put a poll up to see where people are up to. So I have realized in rereading the exercise that it's not quite 100% clear what I'm asking you to do here, because there is the more complex problem. So actually what I meant in this exercise was the simpler problem of just modifying this run benchmark.sh script to take into account nodes as well. There is the more complex problem of how you would modify this launch one so that it worked out when the number of cores you were requesting went over a single node and knew how many nodes to use. That's a more complex problem, and we could look at that if people are interested. But actually, that's not what I was asking people to do here. It was just a more simple task of modifying this script up here. Okay, because that is a bit more complex to get working in Bash, is to get the right number of nodes, get the right number of nodes out for the number of cores that you have. Okay, so most people have managed to do this. So let's have a quick look at the solution then, before we go on to a break. So I'm going to open this here. So it is, I mean, actually quite simple. The modification is pretty simple if you knew what was going on. So you're just capturing 3 variables this time, 3 arguments this time from the command line. One of them sets the number of nodes, and one of them sets the cores and pose, and one of them sets the number of repeats, and then you could use it in this sort of way. So this is 2 nodes, 128 cores per node, 3 repeats. That's 256 cores in total. If you wanted to modify this script so that you could just put in core counts up to whatever you wanted in here, and it would pick the correct number of nodes, that is doable, but it's harder in Bash probably than in some other languages. But it is doable. You can do the challenge in Bash is always managing to do. You can't really do floating point arithmetic, but that doesn't really matter so much here. So we had 256. You'd have to know how many cores were per node, so you could do something like. So we have 256 cores, and we knew there were 128 cores per node. You can calculate that that's 2 nodes by using the built-in arithmetic, built-in integer arithmetic in the Bash shell, and that's probably enough. Because if you go over 256 nodes, I'm hoping it will return. That didn't work. Oh, because it's 2 point something. See, so this is why you need to be careful with the Bash, because it only does the integer arithmetic. So I'd have to go up to 384 to get 3. So you'd have to be careful that your core counts were always multiples of 128 once you went above a node to make this work. Otherwise, you would struggle. Okay, it would struggle to get it right. You can pick out those things. I don't know if there's a modulo in Bash, is there? Oh yeah, there is. So where's the 2557? Yeah, okay. So you could do something with the modular arithmetic as well to work out that you didn't have a perfect divisor, and maybe either just print it out or not bother, or do something different there to make it work out. So that's doable as well. But I'm not going to go into that here. How to do that. Okay, so these here documents are a useful trick if you need to parameterize batch submission scripts for whatever reason. They're quite a simple way to do it. There's more complex ways you could do it using Python and things like that, but I'm not going to do those here. If you're going to do lots and lots of benchmarking, and as I said, you're working with benchmarking studies, or you're doing something much more complex, or building something for a service that you want to build, then you might want to actually stop writing your own scripts and use a framework that already exists. There are a few of them out there. For example, there's a thing we use at EPCC called Reframe, which is a regression testing framework. That came out of the Swiss Supercomputing Center at CSCS, which is a really nice piece of software, and it as well as being able to perform tests and tell you functionally if your system is working or not from a user perspective, or working as expected from a user perspective. It also has the facility to be able to capture performance data and log it. And then, for example, you can run it periodically and log it and look at the output over time and stuff like that. There you go. Look, George has solved this problem, provided the complex bit of arithmetic you need. So that's a really useful tool. We use it at EPCC, and we're developing more and more tests to go into it. The Jülich Supercomputing Center in Germany developed a really quite comprehensive framework called Jube or Juba. I'm not quite sure how it's said properly, but that is quite comprehensive and aimed specifically at benchmarking. Has a lot of options and a lot of customization in the way you can set it up based around XML files and describing what your benchmarks are. And also, there's also the Dakota framework, which came out of I think it was Sandia Laboratories in the US, but I'd have to go and double check. It might be one of the it might be Lawrence Livermore or one of those ones, one of the US supercomputing centers anyway, which supports this because it allows for substitution of parameters in input files, job sizes and things like that. It's actually not really designed, it's not purely designed for benchmark studies. It's designed for more any sort of parameterized study that you want to run on an HPC system, be that some sort of sensitivity analysis or uncertainty quantification, or it can be turned to benchmarking as well.